So welcome everybody joining us on YouTube. This is Monday, April 27th. So we are only a few class periods away from the end of the semester. And today we're going to be finishing up section 3.3. And so the students who are here live, they've been thinking about this problem 3.3.4, which is going to be the start of our what we call applied optimization. And so you can see here it says moving toward applications. And then in our next section, it's all going to be about applied optimization problems. So these are going to be types of problems where you're given some sort of scenario, and you're asked to find some sort of optimal value, optimal situation. And so what we're going to walk through here in this first part is, the general process for solving these optimization problems. And what we're going to find is we're going to have to fall back a lot on our pre-calculus knowledge. Our geometry formulas and maybe some trigonometry to figure out, a lot of the ways to set up these problems. And so I think this first example is a good way to think about that. Okay, so so as we're going, right, so what we want to do is step one, we want to sort of gather all the information that we have from a problem with something like this. Right, so we have this, a 20 centimeter piece of wire is cut into two pieces. We're going to make a square, we're going to make a triangle, and we want to either optimize the area, or either maximize the area or minimize the area of these objects. Okay, and so let me bring up our Blackboard so we can start to record some of this information. So in any type of optimization problem, the first thing that I like to do is draw a picture. Okay, so what we have is we're gonna have some length of wire, right? So it's 20 centimeters of wire, and there's gonna be some place, right? We don't know exactly where that place is, but there's gonna be some place where you cut the wire into two pieces, right? So you're gonna end up cutting it. Right, so you have like a red piece here, and then you have a blue piece over here. Okay, so you're going to break up your wire. You're going to cut it so that you've got a red section of wire and a blue section of wire. And so what we're going to do with those is the red section will make a triangle. So this is blue. So the red section we'll say will make a triangle, and then the blue section will make a square. Right, so you can imagine sort of taking the wire, bending it around into these two shapes. And so our questions become, where should we cut the wire if we're going to maximize the total area or if we're going to minimize the total area, right? So when I come over here, I'm going to see this triangle has some sort of area, and then this square has some sort of area, right? All right, so step one, I've drawn a picture, and I sort of understand the problem, what's going on. And the next thing that I'm going to do is I'm going to assign some variables. So there's going to be some change, something is going to be changing here, right? There's going to be some variable. And so in this particular problem, it's where I cut this, right? So if I were to cut the wire way over here, my red piece would be pretty long and my blue piece would be pretty short. If I cut the wire over here, you can see here my red piece is shorter, my blue piece is a little bit longer. So, but we don't know exactly where that's going to be. It'll be somewhere along the way. And so what we want to do is assign a variable. A lot of the time we use X for that situation. And so in this situation, let's just say from the end, right, from the end of the wire, what I'm going to do, I'm going to measure out some distance X, and then I'll call that X. Okay? So here's the question for you. If that is length X, what's the blue length? Do we need a new variable? Do we need to call it Y, or is there some way that we can figure out what the blue length is? Close. It's not X minus 20, but that's very close. 20 minus X, yeah, right? So how close it is to 20, right? So this over here is going to be 20 minus X. right? So if I add those two things up, then I'll get 20. Okay, so look at all this stuff, right? So we have x here, we have 20 minus x, and so depending on where that is. All right, so what we want to do is we want to think about the area of these things. And so if this is an equilateral triangle, right, then I have to come down here and think about my side lengths, right? So I have to think about my side lengths. And then the same thing over here, I need to think about these side lengths. Okay. So if I'm going to find the area of these, I know that the area of my triangle, right, so this first area, the area of my triangle is going to be 1/2 base times height. And then the area of my square is going to be, you know, the side length squared. You can think about it as length times width if you want, right, since it is a rectangle. So you can see that the parameters here, base, right, I'm going to need to know the length of this base. I'm also going to need to know the height, and then I need to know the sides here. So some of these aren't too bad, right? So if I have a length x and I want to make an equilateral triangle, I'm going to take that side, that distance, that red section, I'm going to cut it up into 3 pieces that are all the same. And so that length is x over 3. And then what I have over here is this is 20 minus x divided by 4, right? So the square over here, the side length is 20 minus x divided by 4. Okay, so 20 minus x over 4, that's my side length here, and it seems like I could very quickly then put together the area of my square. So that's 20 minus x over 4 times 20 minus x over 4. Okay. So that's the area of my square. But then if I come over here for my triangle, if I'm going to find the area of my triangle, a little bit more trouble because this is 1/2 x over 3 times something that I'm not sure about. Okay. So here is our next issue, right? If I'm given a triangle, the side length is x over 3. How tall is that triangle, and how do we know? You could use Pythagorean theorem. Could you use Pythagorean theorem? I suppose you could use the Pythagorean theorem. So, so Caleb, how would you do such a thing? So let's go to an aside here. Right. So we've got our triangle. We've got a side length of x over 3, and then I want to know what is the height. So Caleb, it's a Pythagorean theorem, which tells you that a squared plus b squared equals c squared, right? So it tells you that if you have a right triangle and the hypotenuse is c and the legs are a and b, that a squared plus b squared equals c squared. Right? So how does that apply? How does that apply here?
A would be 1/2 of x over 3.
Okay.
And then c would be x over 3. And then you solve for b.
Okay, so this is x over 6 down here on the bottom.
Yeah.
And then you want to know, and then you're saying this is going to be our b.
Yeah.
Yeah. Okay. So what we get is we get x over 6 squared plus b squared is equal to x over 3 squared. Something like this.
Yeah, looks good.
Okay. So then let's do this out. What happens here, right? So we get so you get b squared is this thing on the right. This becomes x squared over 9, and then x squared over 6 squared. So this is be x squared over 36. Okay. So what happens here? Still guiding us,
You would
Caleb?
square root both sides.
We could, right? So let's get some common denominators there first, right? So we would want to go through this and say get some common denominators. So this becomes 4x squared over 36 minus 1, or just x squared over 36. So you get b squared is 3x squared over 36.
Yeah, and then you just take the square root, right?
Take the square root, right? So this is going to be square root of 3x over 6. All right, so if I take the square root of each part, square root of 3 is just the square root of 3. That doesn't simplify. Square root of x squared is x, and square root of 36 is 6. So far, so good? All right, so what we just walked through was we were finding this height right here. Okay, so if I put all this in, what we should see is, right, we get square root of 3x over 6. All right, so this is one of those things where we haven't actually done like any of this calculus that we've been talking about up to this point, right? All we've been doing is setting up our problem. Okay, so far we have all this information, and are we done yet? I mean, can we go and do some calculus? Right, so we can't just yet, right? So what we want to do is we want to come up with our function, the thing that we want to optimize here. Okay, so what we want to optimize is the total area that's present in our scenario here. So the total area is the area of the triangle plus the area of the square. Okay, so we have to put all of this together, and it looks like we get this is the square root of 3 times x divided by 36. Should be x squared. And then plus, we get this 20 minus x over 4 squared. Okay, and so this is the function that we would like to optimize, right? So what we saw before was in order to find these optimal values, we need to have some sort of interval that we are going to be thinking about. So is there some sort of domain that I should be viewing this function on? Is there a minimum value that x could be, and is there a maximum value that x could be?
It has to be positive.
So x has to be some sort of positive number.
Yeah,
It certainly has to be positive, but there's more to it than that, right? So it has to be positive. It could be 0, right? But is there an upper bound? Like, could it be 1,000, for instance? Like, what's that biggest value that x could be here?
$20.
20, right? So the length of the wire is 20, and then so if it's 0, that means that like we're not making a triangle. The triangle doesn't exist. We're putting everything into the square. And then if x is 20, that means we're going to put nothing into the square, and everything's going to go into the triangle. Okay. So now what we're going to do, since we have all the numbers, we're going to go ahead and we're going to put this into Desmos. But just to recap here, we walked through the process of optimizing here. Okay, so step one, we drew a picture, okay, to organize our situation. Step two, what we did is we assigned some variables to quantities that might change, right? So we assigned these variables and we came up with any sort of relevant information that we needed, right? So step two is this process of putting down quantities, right? So variables or lengths or formulas. And then so step three, what we were doing when we were finding these areas is we were trying to come up with the equation that we wanted to optimize, right? So step three is find this equation and then find some sort of reasonable range that you want to optimize over, right? Where does the problem make sense? Right? And so what we can do now is we're going to take this equation and we can put it into Desmos. Okay, so I have to switch my sharing, right? And so what I have, right, so I have this function, which I'm going to call a of x as I did before, and it's the square root of 3 times x squared. This is all over 36. And then we have this 20 minus x all over 4, and this was squared, right? So we have this function that kind of looks like a quadratic, and then we want to restrict our attention to just a particular range, right? So if I can set up my problem, right, correctly and get those equations, finding the optimal values doesn't seem to be such a challenge when we have such a great tool like Desmos, right? So we have this equation. I want to find the optimal values on a particular interval. And so we can see that, hey, it looks like the maximum area occurs here and the minimum area occurs here, right? So remember, this is our area. My global maximum occurs at this point. My global minimum occurs at down here. So can we make some sense out of these numbers? So while we're here, let's see if we can make a sentence out of these 2 points, right? So this number 0.25, what does that mean? And then this number 11.301, 10.874, what does that mean? Let's take a minute to think about it, and then we'll see if we can share sort of what that gives us. So we get any volunteers about this point right here, 0.25? Want to give us a sentence around this point? What does it mean?
Is that the initial length of the rope or the line, whichever you
Yeah.
call it?
So which number is 0 or 25?
The 25, before you cut it would be the 25 meters. Wait, no, I thought it was 20. I have no idea.
20, right? Yeah. So the wire was 20, right? So we have this. If I input 0, I get 25. That's our max value. So let's go back and look at our picture. Okay. So what is the 0 and what is the 25, right? So if x is 0, if this is 0, what does that mean?
Would it mean that there's no triangle?
Yeah, right. So there's no, you're not even making a triangle. So if you want to have the maximum area, like you shouldn't make a triangle at all. And then you should put everything into the square. Okay, so what we're going to see with these optimization problems, a lot of the times they're going to be phrased in terms of like, hey, a farmer has 20 feet of fencing and they want to create 2 pens, and one's going to be a triangle and one's going to be a square. How do you find the maximum area of the 2 pens or something like that? And so if that was the context, we would advise the farmer, just make 1 pen, don't make a triangular pen, get rid of that thing and put everything you have into the square. That's going to give you the most bang for your buck here. You're going to have the most area if you just make a square and no triangle. Okay. And so that's what the interpretation is, right? So 0, meaning the red length is 0, there's no triangle, and then you could have an area of 25, right? Square units, centimeters here. That could be your area here. Now, on the flip side, if you wanted to minimize, right? So I gotta jump back over here again. So if you want to minimize your value, you're down here at 11.301, right? So not really a particularly nice value, 11.301. And so we would say, hey, if we're going to minimize, we should have, this 11.301. Let's go back to our board. If we're going to minimize the amount of wire that you put into the triangle should be that 11.3, and then only about 8.7 should go into the square. That's going to give you your minimum area, right? So if you were thinking about like you wanted to minimize a footprint or something of these things, you had to create them. That would be the dimensions that you wanted. Okay. So a lot going on here, but I think it's a good illustration of the steps and how we may have to go out and sort of think about, area formulas or Pythagorean theorem or maybe some trigonometry to get all the information that we want in here. All right, so I'm going to kick it over to you all for questions here before I give you just a quick extension here. So this feels okay? Yeah, so far, right, so we didn't actually take a derivative in this problem. So one of the questions that always comes up for me when we do this optimization is, well, if I could just plug this into Desmos, what was the use of having to figure out all these derivatives and do all this stuff with finding the first derivative test and all that. And so where that's going to really come in is when we start having those parameters. Remember, we were talking about families of functions where we had these parameters like a, b, and we had a logistic function that had really a lot of parameters. So we could do this problem where let's say you have L centimeters, right? So maybe you don't know the length that you're given, right? So we don't know exactly how much we have. We have L. It's not necessarily 20. So what would happen here is, a lot of this stuff would change, right? So we have this number up here, 20, right? So I have to move this so I can rewrite. So this would become L minus X, right? So you have some length of wire, and then this down here would become L minus X, and then so with these, right? So these would all become L's, right? In which case, right? So I can't simply just plug it into Desmos, right? I would actually have to figure out, hey, what are the critical values of this and the endpoints, and I would have to check them all against this. So Desmos isn't useless in this situation. It certainly gives us some information. So let's go ahead and let's add a slider capital L in here, and let's look at our function. Okay. Right, it can give us some information, right? So if we had, you know, this length of wire, all of our parameters would change here. And so we would be able to see, right? So this length of wire, let's start it at 20, and let's go up to 100 or something, right? So here's our problem where we had this length of 20, looks something like this. But you know, what if the problem said 30, right? Would we have to redo the whole problem again? You know, so it seems like, hey, our maximum value is still occurring over here at 0. We've got this new minimum value that we don't really know what it is, or we don't really know how to find this. But, you know, let's zoom out some more. Maybe let's make this, you know, 40. Well, it still seems like that maximum is occurring over here. My minimum is down here. So going through this problem, it seems to be suggesting, right, numerically, that we're always going to have that maximum value when we put everything into the square and nothing into the triangle. But if we wanted to find that minimum value, we'd have some more work to do, right? So we wouldn't necessarily know exactly where this minimum value would occur, and that's where we'd have to go through and we would take this derivative, we would find our critical values, check them. Okay, so for the sake of time, I'm not going to walk through that here, but I wanted to illustrate to you how these problems are going to progress in the future, right? So we'll do them numerically, and then we're going to add in a parameter and see if we can, you know, do something more generally where we talk about a family of these types of problems rather than just one individual specific problem. Okay. All right. So if you want to see the whole thing worked out, there is a solution in the book, but we had a function that was a little bit different than that, right? So we had an approach that was a little bit different than theirs here. Okay. All right. So what I want you all to do now is start to think about this next activity. Okay. So so what we're going to do is we are going to do a classic calculus problem. So we're going to find the volume of a box. Okay, so take a moment to read this starting paragraph, and we'll see if we can make some sense out of that. Okay. All right, so has everybody seen a problem like this before? If you haven't, I think it's often very helpful to have a piece of paper or something like this to think about sort of how we would be making such a box, right? So it says you have a piece of cardboard, so I'm going to have this piece of cardboard right here. It's going to be 10 inches by 15 inches, right? So this is not 10 by 15, but can imagine that it was. And we're going to make a box. Okay, so to make a box, what we're going to do is we go into a corner, right? And we're going to cut out a square, right? So you're going to cut a square out of your corner. And what you want to do is you want to do that on each corner, and you want to make them all the same size square, right? So you see what I'm doing here. I'm cutting squares out of the corners, and I'm going to try my best to make them all the same. Right? Undoubtedly, I'm going to fail at this. I'm not measuring, but you'll get a footprint that looks something like this. Okay, And so what you do is you take each of these flaps and you fold them, right? So I'm going to make a fold so that for each one of these flaps, I'm going to fold it up. Okay. So I'll do the same thing here. And I'll do the same thing here, here. And so if you fold up all your sides like this, you would end up creating like a little tray or a box, right? And so notice how this is a box, but it doesn't have a top, right? So in our problem here, this is what we're creating, right? So we're actually creating one of these boxes, and what we want to do is we want to optimize the volume of such a thing. Okay, so how do I find the maximum volume of such a box, and how do I find the minimum volume of such a box? Okay. So what we need to do is we need to set up some parameters, and then we're going to use some calculus. Okay, so what was the first step that we did for the triangle square problem? What was step one? Our picture, right? Yeah. So when we think about this, right, so the activity is going to sort of walk us through how to do this. But step one, right, step one, draw a picture, right? So if we look at this right here, this is what we're going to do. We're drawing a labeled diagram that shows the given information. Okay. All right, so let's do that, right? So let's go ahead and jump over to our Blackboard. Right, so as we saw, right, so as I was sort of making this out of paper, what we're going to do is we're going to look at sort of the footprint of this, right? So you can see here what this looks like, right? So I have these squares cut out of the bottom. So my iPad is doing something funny here. Can you all still see my shared screen?
I just see a black screen that's shared.
Yeah. Okay. And so let's try this again. So you're seeing me right now, right? And not our Blackboard. Yeah. Sorry, we're having minor technical difficulty here. Okay. My iPad just decided it didn't want to share here. Okay. So we're gonna improvise. All right, so you can all see this, right? This is the whiteboard that comes with this thing. All right, so it's not going to be, my handwriting is not going to be as good on this, but we'll do our best. Okay, so all right, so we had a square, right? So we had a piece of paper, and what I did was I went and I cut out squares out of the corners. Okay, so what we're doing here, we're drawing this diagram, and what I would like to do is sort of figure out, you know, what are the dimensions here. So what was given to us was, you know, the piece of cardboard was 15 by 10, okay? And what we're gonna do is so I drew my picture, but now I need to set up a variable, something that changes, right? So what we're given in our problem is we want the box to have a height of at least 1 inch and no more than 3 inches. Okay, so when I look at this diagram, is there somewhere in here that I can define height? Like, where is the height going to be?
It's from like the inside corner of the smaller box to the outside.
So the inside corner of the smaller box.
Yeah, like up.
Like this?
No, the upper right. Like it's hard to.
So Caleb, you can draw on this screen too, remember. If you click annotate, so do you want to, yeah, right? So that distance right there. And notice that's the same as this distance right here, yeah? So this distance that Caleb pointed out, this is the height, right? This is going to be the height of our box, right? So this is h, and then it turns out that since this thing is a square, this is also h here, right? Okay. So we want to add in some more information here, right? So if I draw sort of dashed lines like this dotted rectangle, this is the sort of the base of my, right? So this is the base of my box that we're creating. And what I'm going to need to do is I need to figure out sort of what that base is, right? So if I'm going to have the volume, you know, the volume is, right, so it's the length times the width times the height. Okay, so that's going to be the volume of my box. Length times width times height. So I have height, I said, was h, but now I need to know what is the length, and I need to know what is the width. And preferably, the only variable that I'm going to use is going to be h. Okay, so can you tell me what this, so let's do this in colors here. We'll do something in blue, right? So the blue, that will be my length, right? That's gonna be the length of my box. So I now want to figure out what that is. And then in green, we'll do this in green. This is gonna be my width. So what is the blue and what is the green?
Blue would be L minus 2H, and green would be W minus 2H.
And what are L and W in this case?
Like what color?
Like 15 and 10.
15 and 10, yeah,
Yeah.
right. Yeah. Right, so this is going to be, the blue is going to be 15 minus 2H. And then the green, yeah, it's going to be, like you said, this is going to be 10 minus 2H. Okay, so my volume formula that I get in terms of height is going to be, right, it's going to be the volume is equal to 15 minus 2H. And then my width is going to be 10 minus 2H. And then my height is just going to be H, right? Okay, now the question is, what interval do I want to think about this on, right? So it could be closed, it could be open, but there's some interval. So I have this function that I want to optimize, and I want to do it over some interval.
1 to 3.
Mm-hmm. Right, so we want the minimum height, it has to be at least 1 inch deep, and it can be no more than 3 inches deep. The largest volume be 252. I don't know. Let's find out, right? So let's go ahead and let's plug this thing into Desmos. So I'm gonna switch my sharing here, right? And we'll plug it into Desmos. Okay. So our volume, right? So this is going to be V of H, which was 15 minus 2H times 10 minus 2H times H. Okay. We want to restrict our attention to when H is between 1 and 3. Okay, so we are over here. Okay. So it seems like our maximum volume is going to occur when we have these values. So can we write can we put these into context here? What do these numbers mean? So what do we think? If we have this, what is the 1.962? Yeah, it's the edges of the box, right? So the height, yeah. So this x value is going to be our height, right? So when we have a height of 1.962 inches, we should have a volume of 132, approximately 132 cubic inches, right? So this would be our maximum volume. And so we'd say the maximum volume occurs when we create a height of 1.962 inches. Right, so if we go back, I don't know if I can, our whiteboard is shared here. Okay, so we kept this. All right, so what we want to do, if I wanted to optimize the volume of this box, what I would do is I would go through and I would cut these squares to be 1.962 inches, right? So then when I fold it up, I'm going to create the largest box that I possibly can, right? So so what I wanted to do was, for this problem, I wanted to change this parameter. Unfortunately, we're out of time. But what we'll do next time is we'll ask ourselves, hey, what if we didn't have a 15, right? So what if this wasn't 15? What if this was just, say, L, right? So we had some sort of length. We have a 10 by something sheet of cardboard. Could we optimize that with just an L in there, right? So we would have an L minus 2H, 10 minus 2H, H on this interval, say 1 to 3. And so we could interpret those questions as well. And so if we wanted to, we could do this totally in general, right? So we could also make this a W, and then we could have these different parameters. But I guess on Wednesday, what we'll do is we'll think about this. So between now and then, if you want to think about this problem, right, where we have a parameter in here, how are we going to come back and use calculus to help us solve this problem? Okay, so coming over here to our equation, right? So in our situation, we had L was 15, but we don't always need to have that, right? So we could have L be anything, right? So we could sort of see how this changes over time, right? So it seems like, again, our minimum is occurring down here, but if we wanted to figure out what this maximum was, we might need, right? We might need some calculus to figure out where that point is always going to be. All right, so I apologize for the technical delay here, but yeah, so we'll come in on Wednesday and we'll see how we can use calculus to help us out solving this with the parameter L, and then we'll track this point as it changes for any length. Right, so if you are thinking ahead, what we're going to do is we're going to jump into section 3.4 for the rest of the week, and we're going to work through these activities. So 3.4.1, and then we'll just continue to go through thinking about these different activities. Okay, so typically these are pretty challenging. We're going to set them up, and then you can see that we're going to start introducing parameters, right? Stuff like this here. Okay, so any questions before we call it a day? All right, so remember there's 2 WebWorks open. There were just 10 questions each, so 20 questions by the end of the week, and it's all about this type of stuff. So, so we'll meet back on Wednesday. We'll continue to sort of set up these problems, introduce parameters, and see how we can use calculus to find the optimal values. All right. You too. I'll see you all on Wednesday.